Okay, sorry about being a little slow getting things up and running today. Everybody at home can hear okay? Yeah? All right, so check your inbox. I've sent out a few emails about Exam 1. There's some details there about some questions that you might have. If you didn't do as well on the exam as you thought you did, I've posted a video. The link will be in the email and on the content page of Learning Suite with some suggestions based on observations I've made in previous semesters about what works in this class and what doesn't. So take a look at that. The average score was about 75%. The 50th percentile score was about 79% in general. Though I don't assign grades till the end of the semester, in general, the 50th percentile tends to be somewhere between a B and a B minus, so that may help calibrate you as to your performance. Also, scores in sort of the below the 50th percentile, cutoffs between, say, C minus and D tend to be quite a bit lower than 70%, and so depending on your situation, it may not be as bad as you thought it was. There are a few people who have yet to take the exam because of various accommodation issues and emergencies. And so I won't talk right now today about specific problems on the exam. I will make available within a couple of days. I will make it possible for you to go back in and see the items you missed, see the exam questions, see the correct answers. And I'm wanting to, and we'll try to get this done by then, prepare a little video for each question taking you through how to get the right answer. That way we can answer all your questions as efficiently as possible. We'll also make time later in the week for one-on-one meetings if you want. I probably will send out a link to a Google spreadsheet and you can put your name in a slot and then we'll talk if you'd like to. All right. So I think that may be all we need to do there. Any burning concerns or questions I may have missed? They don't have to be burning. No? Okay. All right. Going forward, if you're looking to improve, maybe you've learned from Exam 1 that this class is more about what you can do and a lot less about what you can remember. Because some of the questions were hard even when you had the ability to look stuff up. So going forward, you need to view your preparation as though it were some kind of training, whether for a musical performance or an athletic event. You're going to want to make time every day, and you're going to want to make sure you're focusing on issues where you are weak. Couple years ago, well, not years ago, in 2019, before the pandemic, we had a state conference where I was asked to play the organ for a choir, and the choir director was very ambitious, and she decided she wanted to do Richard Elliott's arrangement of Let Us All Press On. You can Google it. It's kind of nice. Has this moving organ line in the last verse where your foot's constantly going. I'm not a trained organ player. I'm not that good. I sort of taught myself on my mission when the other elders were playing basketball because I haven't got game. And so leading up to this event, was really stretched for me, and I had to practice. I ended up going into the church on the way to work most mornings and playing for a while. And my practice was most effective when I worked on the things that were really hard to the point that it became muscle memory. And then by the grace of God, it all came off in the end. I made some mistakes, but when you're accompanying, anytime you get through the song and you don't have to stop and say, hold on, wait, that wasn't it, let me try again, it's a win. And so I'll just encourage you as you're preparing for the next exam, use the study guides and practice exams as an indicator for issues, little red flags, issues that you need to fix. Fix them. Spend most of your time fixing those issues, and that allows you to leverage your limited time towards your most vulnerable issues to get the maximum return on the exam. I don't know what leveraging is or hedge funds. My son has really tried to explain to me the GameStop thing, and I am just barely there. Oh, by the way, I have had emails from students feeling guilty about using the internet, notes, lecture videos. All of that was okay, right? So no guilty feelings. You were just not supposed to work with another human. So there you go. Unless the human was me in my YouTube video. I guess that should have been. Anyway. Okay. So we are going to move on to chapter 4, which is kind of fun because we get to talk about the shapes of organic molecules. And let's see, we're recording. Yep. So I'm going to just open up. Oh, there's Among Us again. Guess Adam was trying to play. I'm going to open this Gallery of Molecules app, and we're going to look at our one of our simplest organic molecules that has an interesting shape. And this is ethane, just the 2-carbon ethane. So there we are looking at ethane. Okay. Now by now you should be good at imagining when you just see carbon endpoints on a line, the hydrogens that are implied but not shown. And you should be okay at drawing out a tetrahedral shape using the dashes and wedges. The lines that are straight, now, are in the plane of the page. Dashes are going back into the page. Wedges are coming out at you. However, you may still be a little bit weak on understanding what that means in terms of 3 dimensions. And today we're going to start thinking about molecules not as static images, but as having the ability to rotate around single bonds. As we talk about this, it's going to be useful to introduce a new way of drawing organic molecules, and this way is called the Newman projection. I don't know whoever Professor Newman was or why the projection is named after that person. If you're a Seinfeld watcher, you can, hello, Newman. I actually had a missionary companion whose last name was Newman, but I had not watched Seinfeld before the mission, so I didn't know to harass him with that, which was kind of unfortunate. In retrospect, it would have been nice to have that in my toolbox. But in any case, this is the Newman projection. You're looking down a carbon-carbon bond, and you can't see the carbon behind you because you're looking straight down that bond. In the front, you can see carbon-hydrogen bonds on an sp3 hybridized carbon. They are all, from this perspective, coming out at you, but if you sort of flatten them into 2 dimensions, it looks like they're all in the same plane, and it looks like they're only 120 degrees apart, even though in reality it's a tetrahedral carbon. But when you look at it from this angle, that's what you see. All right. We'll talk about, this is actually a concept from vector math. The angle between a carbon-hydrogen bond in the front, so maybe this one that's green, and a carbon-hydrogen bond in the back, that's called a dihedral angle. And the technical definition for dihedral angle is the angle between 2 vectors. And if you want to calculate it, there's the dot product and so on. We won't care. I just want you to be used to this idea of a dihedral angle, which will be angle between a bond on the front carbon and a bond on the back carbon. So the angle between this carbon-hydrogen bond and this carbon-hydrogen bond in this perspective, the dihedral angle is about 60. Okay. In contrast, the dihedral angle between the proton here, carbon-hydrogen bond there, and then this one in the back is 180. Therefore, we're going to have some words to describe protons that have a dihedral angle of 180 versus protons that have a dihedral angle of 60. The proton in the front here is going to be said to be anti to the proton in the back, ANTI, opposite. That one's easy. Whereas the proton in the front is going to be said to be gauche to the one I'm indicating now, the one where the dihedral angle is 60. So we're going to talk about two groups being gauche to each other. I think I should really slow this down so that, yeah, that's nice. 0 femtoseconds per second. We have gone to absolute zero, folks. This molecule has 0 kinetic energy. You saw it here first, right? The dihedral angle between a proton here on the front and then here in the back, that when it's 60, we will say those two protons are gauche to each other. Is everybody seeing? Oh, I should dim the lights. Folks at home are saying they're not sure they can see what I'm highlighting. If I hold on to it, can you see the green? Yeah. Gouche. Gauche. So I got to hold on to it longer. All right. The relationship between this proton in the front and this one in the back, the dihedral angle is 60 degrees. They are gauche. Folks at home, is that clearer? I tried to hold on to the hydrogens longer. Okay. In contrast, this proton in the front is anti to this proton in the back, where the dihedral angle is 180 degrees. All right? So one of the things that you notice as we turn up the time scale and allow this thing to sort of exist is that, on its own, is that if you look down the carbon-carbon bond in sort of the Newman projection, one of the things you notice is that the protons in front are all in between the protons in the back. That is, each proton is gauche to two other protons and anti to one other proton. Gauche is 60 degrees, anti is 180. This is called the staggered conformation of ethane because each carbon-hydrogen bond in the back bisects or is in the middle of the space between two carbon-hydrogen bonds in the front. Notice how this proton in the back is gauche to these two protons. And we call that a staggered conformation because they're staggered. I don't know how else to say it. Is that sort of clear as mud? Now that differs from an eclipsed conformation, and I don't know how to do this other than I'm going to rotate around this try to rotate around this carbon-carbon bond. Okay, I'm going to pull on one of these hydrogens in the front and try to spin it around. And as you notice it spinning, we're going to do this a couple of times, and I want you to sort of give me a sense for what's happening. Okay, spin it around. Spin it around. Like a record, baby, right, round. Spin it around. There, as we spin things around, we come through a conformation where the hydrogens in the front are lined up with the hydrogens in the back. It only lasts for a split second, so you have to sort of look close and not blink. No, that's not what we wanted. Each time a hydrogen goes around, there it is again. We go through a conformation where the hydrogen bonds in the front are lined up with the hydrogen bonds in the back. Does that make sense? Can you see that? Now, based on what you're observing as I try to spin this proton around, did you notice that? Go ahead.
Sorry, what was that called again? What type of conformation?
Eclipsed. It's called an eclipsed conformation when the protons in the front are lined up with the protons in the back in the Newman projection. Now, did you notice that when we spin this front methyl group around, at first we go through those eclipsed conformations without a lot of trouble. Then as we slow down, I want you to watch what happens, because the proton in the front is going to try to get to an eclipsed conformation and miss, not quite get there, go back down to a staggered conformation, swing back towards another eclipsed conformation, bouncing back and forth, and then settle on the staggered conformation. See if you can observe that happening. I didn't apparently give it enough oomph, so shoot. There we go. There goes the propeller, slowing down, not quite, back. There we go. You see it? Should we do it again? The frame rate is really bad. What am I trying to show? I am sorry about this. We'll diagram it out on paper in just a second. I'm sorry that the movie's not coming through very well. So spinning the molecule around, spinning the methyl group around. Oh, we just barely, and not quite to an eclipse conformation, back and forth, setting into the staggered conformation. All right. So what do you think about the relative energy levels of the eclipsed conformation, where they're all lined up, versus the staggered conformation, where they're all interdigitated? What do you think? You had to say which one was higher. What do you think? Eclipsed is probably higher. Yeah. And if you had to think about the amount of time the molecule spends in staggered versus eclipsed, what would you say? Probably, at least at this temperature, which is 0 degrees Kelvin, it's going to stay at the energy minimum. And it turns out that eclipse conformation is not an energy minimum, it's a maximum, meaning it's a transition state from one eclipse conformation to the next. So here we go, we're increasing energy. We go through a maximum as we get through the eclipsed conformation, and then we get to another staggered conformation. So this may be difficult for folks at home to see. So I'm going to show you how to draw this out on paper, because this is a useful skill. All right, so here is our ethane molecule. And we're going to draw it from the side in the staggered conformation. It may not be clear to you that this is the staggered conformation. Folks at home, can you see the iPad screen now? Okay. You're going to put your eye, you're going to lay down and put your nose in the plane of the board, looking down the bond between carbon 1 and 2. And here, I never can resist. Here are your angry, evil, jaundiced Sith eyes. Who knew that becoming a Sith came with liver disease or kidney disease? Anyway, you're going to look down that bond, and then we're going to draw what we see. So we're going to draw a circle for carbon 1, and we're not going to draw carbon 2 because it's in the back behind carbon 1. Then we're going to draw each carbon-hydrogen bond coming off of carbon 1. And we're going to draw it in the arrangement we see it from this perspective of being in the plane of the page. So hydrogen in a square, we're going to show pointing downward in our Newman projection. And then the other two hydrogens we're going to show angled upward, as though there were as though they were 120 degrees apart, though we know based on our experience that the bond angles are really 109.5 because this is a tetrahedral carbon. We're just looking at it from a perspective that makes it look like everything's smashed down into 2 dimensions. Okay? From our perspective, pink triangle proton should be coming out to our right, and orange circle proton should be coming out, going back to our left. If we look at this molecule as being in 3 dimensions, we'd have to realize that each of these bonds is sort of angled out towards us. All right? Then in the back, we'll do the same thing. I will maybe only label one of these in order to make our discussion a little bit more straightforward. And now I've run out of simple shapes, so I guess I have to do the green star proton. Okay, and the green star proton from our perspective in front of the molecule is gauche to the orange circle proton and the pink triangle proton. The dihedral angle here, we're going to use, let's see, dihedral angle, we're going to use the Greek letter theta for angles of various kinds, equals 60 degrees here. So we are going to say that green star proton, and it sounds like Lucky Charms, actually, or sort of Lucky Charms colors, hearts, clovers, and blue moons. The orange circle proton and green star proton have a 60-degree dihedral angle between them, or we will say that they are gauche to each other. In contrast, the dihedral angle between star green proton and square blue proton is 180 degrees, or we will say they are anti to each other. Yes?
Why not just use the word cis and trans?
Why not just use the word cis and trans? You could say that they are trans with respect to each other, though, and I suppose that would work. Cis maybe is okay, though. I guess we use cis and trans for talking about relationships about double bonds. I think they could work here, but the term anti and gauche will probably be more precise. If you told me this orange proton was cis to the green one, I'd say, yeah, I guess, though when you say cis, it makes me think that they're actually on the same side and overlapped with each other. So you won't, it's not technically, I guess, incorrect. You just won't generally hear organic chemists talk that way.
So when they are cis, does that mean they're eclipsed?
Yeah, we can talk about that. If orange proton and green proton were eclipsed with each other, we might say that they were cis to each other. There's nothing wrong with that, but yeah. There was a question, what the heck is a dihedral angle? A dihedral angle is an angle between vectors. So it's the angle between this line, between carbon 1 and green star proton, and between this other line in red, the angle between sorry, I said this wrong. Carbon 2 is in the back, right? So the dihedral angle is the angle between the two vectors that are highlighted, the bond between carbon 2 and green proton, and the bond between carbon 1 and orange proton. So it's really the angle between those two lines or vectors. As we draw it in the Newman projection. Do we not use dotted and hashed lines in the Newman projection to indicate things are coming forward and back? You could. There wouldn't necessarily be anything wrong with drawing all 3 of these bonds with the triangles on them. It's just that when you draw a molecule in a Newman projection, every organic chemist knows what you're talking about, and they know that those bonds are coming out at you, so it's considered unnecessary. Not wrong. Okay, so is there not any word that we need for the 180 anti thing? This dihedral angle theta between green proton and blue proton is 180 degrees. And we call that anti. So anti and gauche. And then if we were to take orange proton and rotate orange proton and really the whole methyl group in front, but you're going to put your molecular tweezers on orange proton and rotate it by 60 degrees in a clockwise direction. For the sake of our discussion, what would we see? Then orange proton in the front would actually be eclipsed with green proton in the back. And showing this is kind of difficult because it's sort of hard to draw an informative image of two lines being on top of each other where you can still see the two lines. So we do the best we can and sort of offset them a little bit. Here is green star proton, and here is orange proton. I guess we'll keep the other colors as we did. When we rotate orange proton by 60 degrees, orange proton comes up here to be eclipsed with green star proton. Pink proton moves down to be eclipsed with this proton in the back, and blue proton moves over to be eclipsed with that one. So we would call this a staggered conformation, and this is an eclipsed conformation. And you've seen, based on that video, that, is there a term for the angle between triangle and square? Yes, that's just a bond angle. That's looking at two groups that are attached to the same carbon. That is a bond angle. From this perspective, it looks like it's 120, though we know in reality, because this is a tetrahedron, the tetrahedral carbon, that these triangle and square protons are 109 degrees with respect to each other. All right. Okay, so we've talked about how the staggered conformation is lower in energy than the eclipsed conformation. And based on what I showed you in the video, actually, the eclipsed conformation is not only higher in energy, it is a maximum. Okay? It's sort of a barrier to be getting between two staggered conformations. Yeah, this is a new term, conformation. It's not an ordinance of the gospel. It's a shape. Conformation means shape of the molecule. Yeah. Sometimes people will talk about conformational isomers, meaning the same molecule, just different rotation about bonds. They'll often call them conformers or conformations of each other. All of that terminology is okay. And I don't know the origin of the term conformation. I was about to say etymology, but I never know whether I'm saying the thing about words or the thing about insects. Entomology. So I hedge my bets and just don't say the word. My son Nate and I have a running list of, I think they're called malapropisms, which are words that are said incorrectly in funny situations. Most of them come from The Office, as in the time when Michael Scott points out that Phyllis has usurped my position as Santa Claus. Really, really great malapropisms there. But yeah, conformation with an O, not an I. If we were to continue, the maximum is describing it's a maximum in energy. And we're actually going to diagram this out in a second. If we were to continue to rotate orange proton by another 60 degrees clockwise, what we would come up with at that point would be another staggered conformation. It's going to look identical to the one we started at, and indeed, in terms of energy, it is identical. The only reason they look different to us is because we've magically labeled these protons so that we can tell the difference between them. Hold on. Yeah, there we go. Sorry. Got ahead of myself. No, that's right, isn't it? So as we rotate another 60 degrees clockwise with proton that's orange, we move it here to be in another staggered conformation. Triangle proton moves here and blue square proton moves there. We're back to a situation where the dihedral angles all equal 60 degrees, and orange proton is still gauche to green star proton, and it is anti to the proton in the back. With dihedral angles, there are some of you, maybe physics people or math people, who are concerned about sign of angles. Like, I don't mean like the trigonometric sign, I mean the mathematical sign. Some angles are clockwise, some are counterclockwise, some are positive or negative. Don't know the convention, don't care to know the convention. There are maths that do this for us now. So if you know it, good. Don't try to teach it to me because I won't care. You can actually, the bottom line is, if you want to measure the dihedral angle, it's a simple mathematical operation. You define these two vectors, you take their cross product, you divide it by the magnitude and take the inverse cosine of that, I think, and then you've got the angle, and the sign is correct if you do it that way. But see, I didn't care enough to get that right or write it down, so you don't have to worry about it either. So we've gone from one staggered conformation to another staggered conformation. Now, what do you suppose is the relationship in energy between, we'll call this staggered conformation number 1 and staggered conformation number 2? Are they equal in energy? Different? Is one higher than the other? How can you tell? Should be the same. You can tell because they're the same. That's good. They are. And the reason you know that is because they're the same. How many times can we say that? Each hydrogen is gauche to two other hydrogens and anti to one other hydrogen, all the way around. And of course, in reality, we can't tell hydrogens apart. So it's all the same. Which is exactly what we saw in our movie, that when we move and rotate through one eclipse conformation, we get to another staggered conformation that looks just the same as the one we left. All right? And so we could come up with a third staggered conformation that we would get, and I'm not going to draw it for you, but if we rotated through 60 degrees again, we would get another eclipsed conformation. And then if we rotated through 60 degrees again, we would get to staggered conformation 3, where now the orange proton would be anti to the green proton. Yeah? Do we always rotate the front? No. Just for the sake of consistency, that's what we're doing. You could just as easily have decided to rotate in the back. Yep. Others? Yeah.
So we said like these ones are all the same energy, but are there like different conformations where instead of like the hydrogen you have like chlorine or something, then it will be a different energy depending where you rotate it? Or
Yeah. So the question is, under what situations do we get staggered conformations with different energies? We have to replace at least one hydrogen on the front carbon and the back carbon with something else, and then the conformations are not equal in energy. So maybe we can just illustrate this. Let's see, someone asks, is it always a clockwise rotation? No, I just chose for it to be that way because of, just for the sake of discussion. This molecule is the same from either perspective. It doesn't matter whether you rotate one clockwise versus counterclockwise, it's exactly the same thing. Why is the staggered conformation more stable? Excellent. I'm very glad somebody has asked us that. I'm going to hold off on this question about different energy conformations for just a second. So yeah, why? What do you think? You saw that it is, right? You saw in the movie that as we get ever closer to that eclipse conformation, it slows down a little bit like you're getting to the top of a roller coaster, and then you pass through, and then it speeds up to the next eclipse. Yeah, or staggered. Does it have to do with orbital overlap? Yes, it does. So what does the eclipsed conformation mean? It means that all the carbon-hydrogen bonds in the front are overlapped with or eclipsed with the carbon-hydrogen bonds in the back. Or alternatively, the conformation where the dihedral angle between this carbon-hydrogen bond in the front and this carbon-hydrogen bond in the back equals 0. That's what the eclipsed conformation means. Now, why should eclipsed be less stable? There's a couple of things going on here. And both of them have to do with orbital overlap. In the eclipsed conformation, you have repulsive overlap between filled orbitals. And let's just say repulsive side-to-side overlap between filled orbitals. All right? Let me just copy this, and then we're going to draw what we mean by that. And we're just going to choose, we're going to stick in our discussion with talking about the orange and the green protons. So, oops, I didn't mean to erase all of that. So we can ditch pink and blue. They're very sad, but them's the breaks. So here's our here's our eclipsed conformation. And notice that in the eclipsed conformations, the sigma bond in the front is overlapped with the sigma bond in the back. Now let's draw for a minute what that sigma bond looks like. I'm going to use now color not to represent orange proton versus green proton. Color choice could probably be better. Okay, fine. Let's make it better. We'll choose pink for one sign of the wave function, and then, I don't know, blue, since we like babies, pink and blue, I don't know. That is the filled sigma bonding orbital for the carbon-hydrogen in the front. And then here is the filled sigma bonding orbital for the carbon-hydrogen in a bond in the back. Not shown is the smaller lobe on the back one, but that we can't really see. I guess we could sort of draw it there. This is what we would see if we looked down that carbon-carbon bond. And if we actually drew this carbon-carbon bond from, or rather this molecule from the side in the eclipsed conformation, you can tell it's eclipsed because the two carbon-hydrogen bonds we're talking about are both just straight lines. They're both in the plane of the page, right? And if we draw those sigma bonding orbitals, one would be here and the other would be there. Now, we've told you before that orbitals can mix when they are lined up either end on end, that's called sigma overlap, or side to side, which is called pi overlap. So there's some side to side overlap here between the carbon-hydrogen sigma bond here that is filled and the carbon-hydrogen sigma bond here that is filled with electrons. Maybe I'll just use those two symbols to indicate that both of those orbitals are filled. Now, think back to your early, but many, many minutes ago in terms of our thinking about chemistry, understanding of mixing orbitals together. We said when you mix two orbitals together, you mix them to get a lower energy one and a higher energy one. But we said that the higher energy one is always what in relationship to the lower energy one? If we think about this distance, which is the energy the stabilization you gain by mixing the two orbitals together, the higher energy orbital is destabilized by even a larger amount, right? This is why we said that helium doesn't form bonds, because if it did, it comes with 2 electrons, and you would populate both the lower energy orbital and the higher energy orbital, and overall, you would get destabilization. Okay? This is something that in physical organic chemistry is called closed shell repulsion. What it means is when we line up the sigma bonds with each other and they mix a little bit, the electrons in them, some go lower, 2 of them go lower, but 2 of them go even higher, and that's overall destabilization. So getting to that dihedral angle where the 2 bonds are eclipsed with each other takes you through this high energy mixing situation, and it's unfavorable. Okay? A simpler way of understanding that is how your text puts it. Your text talks about something called steric repulsion, and another term that your text uses is torsional strain. And all this means, from your text perspective, is that electron pairs repel each other. Coulomb's law, like charges repel. And when in the eclipse conformation, the electron pair in this bond is closer to the electron pair in this bond than it would be in the staggered conformation. So whether you think of it in terms of closed shell repulsion between filled orbitals, or just basic Coulombic like charge repulsion, either way you get to the same answer, that the eclipse conformation is higher in energy. Go ahead.
So why does it not break the bond since the higher energy orbital?
Why doesn't it break the bond? Well, that's a great question. Each of these are already bonds, so we're talking about an interaction between 2 molecular orbitals that are already there. And what we're saying is we don't get any benefit. In fact, it's bad to have them lined up parallel to each other. Yeah. And that's why there's no bond to break, but what it means is when you get to the eclipse conformation, you don't stay there because it's high in energy. Right? So summarizing, when 2 sigma bonds overlap side by side, there's repulsion. Some of them are destabilized, yes. It's technically, these orbitals that we're starting with are sigma bonding orbitals already, so we're just mixing the 2 together. We don't need to think about the one here being bonding and this one being anti-bonding. We just need to think about the interaction between these 2 sigma bonding orbitals, and 2 of their electrons go down and the other 2 go up by a higher amount. All right? That's the problem with the eclipse conformation. Why does it not stay there if it's high in energy? Well, remember, high in energy is in chemistry, as in life, you want lower potential energy. Systems will spontaneously rearrange to get lower potential energy. So let's talk about another reason why staggered is more favorable than eclipsed. And this is going to allow us to introduce fun new orbital consideration, which is going to appear again and again in this class, and which we are going to use again and again to justify why things happen. In fact, some students have basically decided that this term we're going to talk about, hyperconjugation, is the answer to everything, which it's not, but they figure that if you give it a try, you'll be right more often than wrong. So guess what? Some distracting answers are going to be on the next test. They're going to have hyperconjugation in them. I am evil, but I tell you my evil tricks. Okay. Somebody's asking, how would the conformation change if one of the protons was replaced with a heteroatom? We will get there. We might have to wait until next time. So let's concentrate now on, this is the eclipse conformation. Let's draw the sigma bonding orbital on the carbon for this CH bond in front. And notice that in the staggered conformation, that bonding orbital is as far away as it can get from the bonding orbitals for the CH bonds in the back. There's no farther away you can get. All right? So that minimizes the steric repulsion. I'll just again remind you that this is a filled carbon-hydrogen sigma star bonding orbital. However, let's now think about this proton that, which is in the back. I don't know what color we're going to give it. We didn't give it a color earlier on. And we're running out of shapes. So, diamond, yellow diamond proton in the back. Ooh, okay. This is now anti to orange triangle proton. And I want you to think about the sigma star for this carbon hydrogen that is carbon hydrogen bond that is anti to orange hydrogen. Let's think about its sigma star. What does a sigma star look like? If I just put a carbon here and a hydrogen there, what would my sigma star look like? Node in the middle, lobe here, small lobe there, larger lobe there, and opposite wave function signs every time we go through 0. Notice the interesting observation that a lot of this sigma star projects exactly opposite where the carbon-hydrogen bond is. If we were to draw that on our Newman projection, we would see a node here. We would see a lobe going in this direction, one here, and then a larger one there. So you've got a filled orbital in the front, and in the back you've got this empty sigma star. And it may help for you if we view this from the side. So here we'll say it's not perfectly from the side. We've had to make an adjustment, but hopefully this will make things clearer. Here is orange triangle proton and yellow diamond proton. Here is the carbon-hydrogen sigma bonding orbital. It is filled with electrons. And let's see, I need blue. And then here is the filled, dang it. Oh no, it's okay. Nothing was ruined. Here is the node. Here's the empty sigma star anti-bonding orbital. I'm going to fill in the wave function signs with color. I have, from this perspective, a filled sigma orbital and an empty sigma star, and they can line up perfectly for side-by-side overlap. Now, above, side-by-side overlap of two filled orbitals was bad. The thing that makes this okay and even good is that you've got side-by-side overlap of a filled orbital with an empty sigma star. Okay? Now, you are right to think, how can that be? Because the sigma star is high up in energy. And it is true that energy difference between sigma and sigma star means these orbitals don't mix that much. They mix a little bit. And that mix is enough to bring these electrons lower in energy by about 1 kilocalorie per mole. It's not a lot, but it's enough to make the staggered conformation even more stable than the eclipsed conformation. Of course, there's a higher energy empty orbital up there that remains empty, and the electrons in the lower energy orbital stay lower in energy. You can think of this as though it's sort of partial delocalization into the antibonding orbital. So that's the other explanation for why staggered is more stable than eclipsed. We'll review that next time, and then we're going to talk about what happens when we replace the hydrogens on the front and the back with something else.